In 1996, if you wanted to capture a real scene and look at it from a new angle later, you needed a motorized camera gantry, hours of capture time, and gigabytes of storage. Gigabytes in 1996. And even after that effort, you could only move your virtual camera within the scene about the size of a shoebox. With modern 3D reconstruction, these days, you can walk around the objects you want to capture with your phone for a minute or two, take a coffee break, waiting for your model to finish running, and then explore the photorealistic reconstruction in real time with 6 degrees of freedom. The goal is the same. In fact, the math underneath it is also the same. The framing is different. What changed was the representation and the way that we represent the scene and encode all of this data and the algorithms used. This is the clearest example of how a research field actually moves, not in a straight line, but actually a pendulum that swings. We're going to walk through the history of image-based 3D reconstruction. There are 2 brute force methods for doing this, and both of them are terrible, in fact. The first is to capture every possible photo of the scene that you can. Every position, every angle, every possible view. That requires infinite amount of storage and infinite amount of capture time, which is not realistic. The second is to completely reverse engineer the scene. Recover the geometry, recover the material, find all the reflections, and everything else that is in the scene, and then rebuild it with classical renderer. It's basically simulate everything. In theory, that gives you complete control, but in practice, every stage of doing this is fragile. Every method in this field lives somewhere between those 2 extremes. And the history of novel view synthesis is largely the history of moving back and forth along this axis. Underneath all of these methods is the same mathematical object. Imagine a function that tells you what light arrives at any position in the space from any viewing direction. All the light everywhere, from every direction. Vision scientists call this the panoptic function. I'm giving it a full video of its own, which is our next video. So for today, we are just gonna name it and explain it as part of this bigger idea. So in empty space, away from any occluders, this function can be reduced to 4 dimensions. 4 numbers that identify a single ray of light. That 4-dimensional object is called a light field. So if we state it honestly, novel view synthesis is reconstruct a function you can never completely capture using a sparse collection of 2D samples of it, well enough to fool human eye. That is what this field is trying to do. So hold on to this framing, because every method that we're going to talk about here is an answer to the same question. How should we interpolate the panoptic function for the missing parts? So the first major bet arrived in 1996, actually twice. 2 different papers, almost the same time. Light field rendering from Stanford and Lumigraph by Microsoft. Their bet was so radical on one side of the spectrum. They were like, skip geometry instead of reconstructing the surfaces, and let's parameterize every ray by where it crosses 2 parallel planes. 2 coordinates on the first plane and 2 coordinates on the second plane give you an index to a ray. So to render a new view, what you do is simulate light. You look up the stored rays closest to the ray you need for the new view and interpolate between them. Rendering becomes a database query, basically. And this gives light fields a property that still feels remarkable. Rendering cost is almost independent of the scene complexity. A forest or a single teapot can roughly cost the same to the renderer because you are not tracing geometry or simulating materials. You are rendering from a database. Unfortunately, the database is also the problem. Interpolation only works when neighboring rays contain similar information. And that only happens when the scene has been sampled very densely. If your samples are too If your samples are too apart, rays that appear close in parameterization may actually hit different objects. Blend them together and you get ghosting or double edges and broken depth. So these systems needed camera arrays, motorized gantries,